This is SpaceTime Series 25, Episode 135. Coming up on SpaceTime, astronomers identify a paradigm-changing cosmic explosion, how Saturn's rings and tilt could have been caused by an ancient missing moon, and the Kremlin launches a new spy satellite. All that and more coming up on SpaceTime.
Welcome to Space-Time with Stuart Gary.
Our standard astronomy textbooks will need to be rewritten after scientists discovered a distant blast unlike anything they've ever seen before. The event, which occurred back on December the 11th last year, was a gamma-ray burst about 1 billion light-years away. It was detected by NASA's Earth-orbiting Swift and Fermi space telescopes. Gamma-ray bursts are the most powerful explosions in the known universe since the Big Bang 13.82 billion years ago. They're so bright they're visible halfway across the universe and release as much energy in a second as our sun will generate during its entire lifetime. For the last few decades, astronomers have generally divided gamma-ray bursts into two categories. Long-period gamma-ray bursts, those lasting 2 seconds or more, are generated by the supernova explosions of the most massive stars. As these stars collapse in their death throes, they crash down to form stellar mass black holes. Short-period gamma-ray bursts, those lasting less than 2 seconds, are generated by the merger of superdense stellar corpses called neutron stars, also resulting in the formation of a black hole. Scientists sometimes observe short bursts with a following flare of visible and infrared light called a kilonova. However, in this new discovery, astronomers have identified a burst, which they've catalogued as GRB 211211A, which has proven to be a paradigm-shifting event, the first long-duration gamma-ray burst that's been traced to a neutron star merger. Multiple teams of scientists have studied this unusual event, reporting their findings in journals Nature and Nature Astronomy. The authors found the high-energy blast lasted about a minute, with follow-up observations leading to the identification of a kilonova. The discovery has huge implications for how some of the universe's heaviest and most valuable elements came into being. A classic short gamma-ray burst begins with two orbiting neutron stars, the crushed remnants of massive stars that have exploded as supernovae. As the stars circle ever closer, they strip neutron-rich material off each other. And they also generate gravitational waves, ripples in space-time. And there's the first conundrum. None were detected from this event. Eventually, the neutron stars collide and merge, creating a cloud of hot debris emitting light across multiple wavelengths before quickly collapsing inwards to form a stellar mass black hole. Scientists hypothesize that jets of high-speed particles launched by the merger produce the initial gamma-ray flare before they collide with the wreckage. Heat generated by the radioactive decay of elements in the neutron-rich debris likely create the kilonova's visible and infrared light. And this decay results in the production of heavy elements like gold and platinum. The authors say the kilonova generated by this event is positive proof that connects mergers of these long-duration events, forcing astronomers to rethink how black holes are formed. Both the Fermi Space Telescope and the Swift Space Telescope detected the burst simultaneously, and Swift was also able to rapidly identify its location in the constellation Bootes, and that enabled other facilities to quickly respond with follow-up observations. Those observations have provided the earliest look yet at the first stages of a kilonova. Many research groups then delved into the observations collected by Swift, Fermi, the Hubble Space Telescope, and others. Some have suggested that the burst's oddities could best be explained by the merger of a neutron star with a stellar mass black hole. And the event is also relatively nearby, at least by gamma-ray burst standards, which may have simply allowed telescopes to catch the kilonova's fainter light. But this light following the burst, called the afterglow emission, also exhibited unusual features. Fermi detected high-energy gamma rays starting about 90 minutes after the burst and lasting more than 2 hours. And these gamma rays reached energies of up to 1 billion electron volts. Now, by comparison, visible light's energy measures between 2 and 3 electron volts. This is the first time astronomers have seen such an excess of high-energy gamma rays in the afterglow of a merger event. Normally, the emission decreases over time. It's possible that these high-energy gamma rays came from the collisions between the visible light of the kilonova and electrons in particle jets. These jets could be weakening ones from the original explosion, or they could be new ones, powered by the resulting black hole or magnetar. Scientists think neutron star mergers are a major source of the universe's heavy elements. They base their estimates on the rate of short bursts thought to occur across the cosmos. But now they'll need to factor long bursts into their calculations as well. This report from NASA TV.
An unusual outburst about 1 billion light years away has rocked scientists' understanding of the universe's most powerful events. Some of these are the source of heavy elements in the cosmos, like gold. For decades, scientists have divided these explosions, called gamma ray bursts, into two groups, long and short GRBs. Long bursts produce a flare of gamma rays, the highest energy form of light, that last 2 or more seconds. They're thought to be caused by the black holes forming at the center of massive collapsing stars, and are followed by supernova explosions. Short bursts, on the other hand, last less than 2 seconds, and are likely caused by neutron star mergers, and are followed by flares of visible and infrared light called kilonovae. But a recent event has scientists rethinking these categories. On December 11th, 2021, NASA's Swift and Fermi telescopes observed a 50-second long gamma ray burst, followed by the clear signs of a kilonova. It's called GRB 211211A. It was later studied by the Hubble Space Telescope, along with a number of other observatories. Scientists don't yet know how a burst caused by a neutron star merger produced gamma rays for so long. Maybe, instead of 2 neutron stars, one of the objects was a black hole. Kilonovae are a known source of heavy elements like iodine, which was essential for the development of life on Earth. But scientists thought that they were only associated with short bursts. GRB 211211A shows, for the first time, that kilonovae can accompany both long and short bursts. After 50 years of studying these events, scientists are still learning new things about their effects on the cosmos.
This is SpaceTime. Still to come. A new study suggests the majestic ringed world of Saturn may owe its spectacular ring system to an ancient missing moon. And the Kremlin has launched a new highly classified spy satellite. All that and more still to come on SpaceTime. A new study suggests the majestic ringed world of Saturn may owe its spectacular ring system and tilt to an ancient missing moon. The findings, reported in the journal Science, are based on new computer simulations which refute previous suggestions that Saturn's 26.7-degree tilt was caused by gravitational interactions with its distant neighbour Neptune. Saturn precesses like a spinning top at nearly the same rate as the orbit of Neptune. And so scientists speculated that the ice giant may well have influenced Saturn's tilt and spin in the past. But the new modelling shows that while the two planets may well once have been in sync, Saturn has long since escaped Neptune's pull. The new work proposes that Saturn, which today hosts 83 known moons, once harboured at least one more, an extra satellite which they've named Chrysalis. Together with its siblings, Chrysalis orbited Saturn for several billion years, pulling and tugging on the planet in a way which kept its tilt in resonance with Neptune. But around 160 million years ago, Chrysalis became unstable and slowly moved too close to Saturn, eventually passing its Roche limit, where it was then totally ripped apart. The loss of the moon was enough to remove Saturn from Neptune's grasp and leave it with its present-day tilt. The study's authors speculate that while most of Chrysalis's shattered body may well have impacted with Saturn, a fraction of its fragments could have remained suspended in orbit, eventually breaking into small icy chunks that would go on to form the planet's signature rings. The missing satellite, therefore, could explain two long-standing mysteries. Saturn's present-day tilt, and the age of its rings, which were previously estimated to be about 100 million years old, much younger than the planet itself. The study's lead author, Jack Wisdom from the Massachusetts Institute of Technology, MIT, says just like a butterfly's chrysalis, the satellite was long dormant, but then suddenly became active and the rings emerged. In the early 2000s, scientists put forward the idea that Saturn's tilt was the result of the planet being trapped in resonance gravitational association with the planet Neptune. But observations taken by NASA's Cassini spacecraft, which orbited Saturn between 2004 and 2017, put a new twist on the problem. Scientists found that Titan, Saturn's largest moon, was migrating away from Saturn at a faster rate than expected, about 11 centimeters per year. That's almost 4 times faster than what the Earth's moon is moving away from the Earth. Titan's fast migration and its gravitational pull led scientists to conclude that the moon was likely responsible for tilting and keeping Saturn in resonance with Neptune. But this explanation hinges on one major unknown, Saturn's moment of inertia, which is how mass is distributed inside the planet's interior. You see, Saturn's tilt would behave differently depending on whether more mass is concentrated at its core or towards the surface. So Wisdom and colleagues used Cassini's final observations during its so-called grand finale suicide plunge into Saturn's thick atmosphere to help pin down the gas giant's moment of inertia. During this death dive, designed to prevent Cassini crashing into one of Saturn's moons and contaminating any potential life there, the spacecraft made an extremely close approach designed to precisely map the gravitational field around the entire planet. Now, the gravitational field can be used to determine the distribution of mass in the planet. The authors modeled the interior of Saturn and identified a distribution of mass that matched the gravitational field that Cassini observed. Surprisingly, they found that this newly identified moment of inertia placed Saturn close to but just outside the resonance with Neptune. So the planets may once have been in sync, but are no longer so. Wisdom and colleagues then went searching for ways of getting Saturn out of Neptune's resonance by using simulations to evolve the orbital dynamics of Saturn and its moons backwards in time, in order to see whether any natural instabilities among the existing satellites could have influenced the planet's tilt. However, the problem there is they came up empty. So they re-examined the mathematical equations that describe a planet's precession, which is how a planet's axis of rotation changes over time, like the gradual movement of the apex of a spinning toy top. Now, one term of this equation involves the contributions made by Saturn's many moons. Now, after a lot of trial and error, Wisdom and colleagues determined that if Saturn's present tilt is a result of being in resonance with Neptune, then the loss of a moon about the size of Iapetus, Saturn's third largest moon, would be enough to cause Saturn to escape the resonance. So, based on this model, somewhere between 200 and 100 million years ago, a Saturnian moon, now called Chrysalis, must have entered a chaotic orbital zone, experienced a number of close encounters with Iapetus and Titan, and eventually came too close to Saturn in a grazing encounter that ripped the satellite apart, leaving a small fraction to circle the planet as a debris-strewn ring system. The loss of Chrysalis not only explains Saturn's precession, it also explains its present-day tilt and the late formation of its spectacular ring system. The story of Saturn and its rings is covered in detail in the current edition of Australian Sky and Telescope magazine. To find out more, we're speaking with the magazine's editor, Jonathan Alley.
Stuart, Saturn's rings, as you say, are really, really beautiful, really pretty. There's nothing like seeing Saturn through a telescope, and you look at these rings and you think, wow. And when you look at them, they look big and substantial, but they're actually really thin. They're spread out a long way, but if you saw them side on, they're actually really thin. And there's long been a debate about the origin of these rings. Where did they come from? Why are they there? How did they form? And basically it boils down to two options. One is that they were formed when a moon of Saturn disintegrated and all the material then spread out in orbit around the planet in sort of a thin ring or multiple rings just sort of going around the middle of the planet. The other idea is that they were formed when material that would normally have gone to make up a moon was prevented from doing so by sort of gravitational effects, tidal effects between Saturn and some of its other moons perhaps. And so this material couldn't form into a moon and then sort of spread its way around the planet, form these nice rings. So they've been the two main ideas for years and years and years. Now there's a new twist on the destroyed moon idea. So some astronomers have proposed that Saturn might once have had an extra moon, which they've called chrysalis, is the name they've come up with, that had what they call some close orbital encounters with two of Saturn's other moons, Titan and Iapetus. Now, these close encounters might have pushed this hypothetical moon, Chrysalis, too close to Saturn, where tidal forces then tore it apart. Yeah, if you get to, it's a sort of a, for any planet, there's a distance from it where if you hang around the distance too long, if you're a moon, you might end up disintegrating. So that could have happened here, and the resulting debris from this disintegrated moon would have spread out to form the rings. And they suggest that this might have happened about 100 million to 200 million years ago. That would match what other astronomers think is actually the likely age of the rings. Part of the debate about the rings is how old are they? Have they been around for a long, long time in space terms, or are they fairly new in space terms? 100 million to 200 million years ago is fairly new in space terms. And one of the reasons that's been suggested is that the rings are nice and bright. They're very shiny. They reflect a lot of light. And some astronomers, or many astronomers, think that the older a ring system like that would get, the rings would become darker.
Yeah, if you look at all the other
sort of chemical effects.
Yeah, if you look at all the other gas giants in our solar system, they all have dark ring systems.
Darker ring systems, yeah. So that's the sort of young ring hypothesis, that they look nice and shiny and bright and new in sort of space terms, space age. That could be right. Now, if this moon had been there and it disintegrated and everything, then disintegration of the moon would have changed what you might call the dynamics of the overall Saturn system, resulting from the moon's destruction, and it would have actually changed Saturn's axial tilt, which sort of matches what they see. And it would also have changed Titan's orbit as well, because you would then sort of removing the gravitational influence of that moon, or spreading it out if the destroyed moon then sort of became the rings. So that's what they're suggesting. Now, not everyone agrees with this overall concept, because it sort of does hinge on this moon destruction event matching the suggested age of the rings. And not everyone does agree with this whole idea that the rings are only 100 million to 200 million years old because they're nice and shiny and bright. So it remains an interesting but unverified hypothesis for now. But I guess it's one of those things we're not going to solve, I don't think. At least I can't really see how. The only way I think we could ever solve this is if we get telescopes that are really good enough, big space telescopes perhaps, to be able to see this sort of thing happening in another planetary system out there in space, perhaps a nearby one. If we can get telescopes that are good enough to see, even in very basic or rough form, a moon or even a planet circling a star being ripped apart and then spreading out, that would sort of give us a good verification that this sort of thing happens. And then whether it happened in the case of Saturn to form the rings, who knows? But anyway, it's interesting stuff.
It's expected to happen to Phobos around Mars in about, 20,000 years? Just got to wait.
That is true. That is true. So Mars has these two small potato-shaped rocky moons, and Phobos is, in space-time terms, is not long for this world or for that world, and could get ripped apart and form a ring around the planet. And it probably even happened to Earth in the past, So it could be a very common thing. It's just that, or at least a common thing over the enormous periods of time that we're talking about in the history of the universe. So you sort of have to be lucky to spot one that's either happening or just happened. When I say just happened in inverted commas, only a few 100 million years ago. So the more sort of examples and samples you have of what's happening with planets and rings and things, the better you can get an idea about it, which is really why it's great to live in this era of the world when we're discovering all these planets circling other stars and getting better and better data and hopefully better and better pictures as the years go by. And we might see more and more of these things in the process of happening or having just happened or about to happen. So it's all grist for the mill.
That's Jonathan Alley, the editor of Australian Sky and Telescope magazine. And this is SpaceTime. Still to come, the Kremlin launches a new spy satellite, and later in the science report, a new study confirms that humans and cats have been together for nearly 10,000 years. All that and more still to come on SpaceTime. The Kremlin's launched a new classified spy satellite designed to intercept radio signals and other electronic intelligence information. The Lotus S1 number 6 was launched aboard a Soyuz 21B rocket from the Plesetsk Cosmodrome 800 kilometers north of Moscow. The Electronic Signals Intelligence Gathering spacecraft joins a constellation of 6 other Lotus satellites. The Lotus series are designed to replace the older Soviet-era Selena and USPM series surveillance satellites. Interestingly, a series of unidentified secondary payloads were deployed by the satellite once it reached its 900-kilometre high orbit. It's thought these could be tasked with spying on satellites operated by other nations. Just 3 days earlier, the final GLONASS M-series spacecraft in Russia's satellite navigation network was successfully launched aboard another Soyuz 21B rocket, also from Plesetsk. The satellite, officially designated Cosmos 2564, was placed into a 19,000-kilometre high orbit. It's the 61st and final satellite in the GLONASS M series. The first was launched back in 2003. The GLONASS M series are now slowly being replaced by the newer GLONASS K variant, which first flew in 2011. GLONASS is the Kremlin's equivalent to America's GPS Global Positioning System, Europe's Galileo satellite navigation system, and China's Beidou constellation. Moscow's been accelerating its own space program in recent months in order to cover over the sweeping bans imposed by other countries on the use of Russian rockets in the wake of the Kremlin's brutal attacks on Ukraine. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.